Welcome to our exploration of decision boundaries in machine learning. Imagine you're teaching a computer to distinguish between apples and oranges based on their features like color and size. The computer needs a way to decide where the apples end and the oranges begin. This is where decision boundaries come into play. They are the invisible lines or curves that separate different classes in your data. In this video, we'll break down what decision boundaries are, why they matter, and how they shape the way machine learning models make predictions. Let's start by understanding the basics. Decision boundary is a surface that separates different classes predicted by a model. For example, if you have a scatter plot of red and blue dots, the decision boundary is the line or curve that divides the red dots from the blue ones. It's the model's way of saying everything on this side is class A and everything on that side is class B. The shape and position of this boundary depend on the data and the algorithm used. Understanding decision boundaries helps us see how a model makes its choices. Make decision boundaries easier to grasp. Let's visualize them. Picture a two-dimensional plot with points representing different data samples. When we train a model, it draws a line or curve to separate the classes. For simple problems, this might be a straight line. For more complex data, the boundary can twist and turn. Visualizing these boundaries helps us understand how well a model is learning and where it might make mistakes. Machine learning models like logistic regression or linear support vector machines create linear decision boundaries. This means the boundary is a straight line, plane, or hyperplane depending on the number of features. Linear boundaries work well when the classes are easily separable. However, if the data is more complex, a straight line might not be enough to separate the classes accurately. When data isn't easily separated by a straight line, we need nonlinear decision boundaries. Models like decision trees, k-nearest neighbors, or neural networks can create complex curved boundaries that adapt to the shape of the data. These models are powerful for handling real-world problems where classes overlap or have irregular shapes. In classification tasks, decision boundaries are crucial. They determine how a model assigns new data points to different categories. If a new point falls on one side of the boundary, it's classified as one class. If it falls on the other, it's classified differently. The accuracy of these boundaries directly affects the model's performance. Sometimes, a model creates a decision boundary that's too complex, fitting every tiny detail in the training data. This is called overfitting. While the model performs well on the training set, it may struggle with new, unseen data. Overfitting often results in wiggly, irregular boundaries that don't generalize well. On the other hand, if a model's decision boundary is too simple, it might not capture the true patterns in the data. This is called underfitting. The model misses important distinctions and makes more mistakes. Finding the right balance in the complexity of decision boundaries is key to building effective models. The features you choose for your model have a big impact on the shape of the decision boundary. More informative features can help the model draw clearer boundaries. Sometimes, adding or transforming features can turn a messy, nonlinear problem into one that's easier to separate. In real-world problems, data often has many features, not just two. Decision boundaries in high-dimensional spaces become hyperplanes or complex surfaces. While we can't easily visualize these, the concept remains the same. The model separates classes using boundaries in the feature space. Support vector machines, or SVMs, are powerful models that find the optimal decision boundary between classes. SVMs look for the boundary that maximizes the margin or distance between the closest points of each class. This approach helps the model generalize better to new data. K-nearest neighbors, or KNN, creates decision boundaries based on the majority class among the nearest neighbors of a point. The boundaries can be very irregular, adapting closely to the data. KNN is simple but can be sensitive to noise and outliers. Decision trees split the data into regions using axis-aligned boundaries. Each split creates a new branch and the final leaves represent the predicted classes. The resulting boundaries are often boxy, following the feature axes. Trees can handle both linear and nonlinear problems. Neural networks can learn highly flexible decision boundaries. By stacking layers of neurons, they can model complex nonlinear relationships in the data. This makes them suitable for tasks like image and speech recognition where simple boundaries aren't enough. Some models create hard boundaries where each point is clearly assigned to one class. Others, like probabilistic models, create soft boundaries assigning probabilities to each class. Soft boundaries are useful when there's uncertainty or overlap between classes. When there are more than two classes, decision boundaries become more complex. The model must separate each class from all others, often resulting in multiple intersecting boundaries. Techniques like 1v's rest or 1v's 1 help manage multiclass problems. There are many tools and libraries that help visualize decision boundaries, such as Matplotlib and scikit-learn in Python. These tools let you plot your data and see how different models draw boundaries, making it easier to understand and debug your models. The complexity of a model affects the shape of its decision boundary. Simple models create simple boundaries while complex models can fit intricate shapes. It's important to match the model's complexity to the problem to avoid overfitting or underfitting. Regularization is a technique used to prevent overfitting by controlling the complexity of the model. By adding penalties for overly complex boundaries, regularization helps the model generalize better to new data, leading to smoother, more reliable decision boundaries. The distribution of your data affects where the decision boundary falls. If classes are well separated, the boundary is clear. If they overlap, the boundary becomes less certain. Understanding your data's distribution is key to interpreting decision boundaries. Outliers are data points that don't fit the general pattern. They can distort the decision boundary, especially in sensitive models like KNN. Handling outliers through preprocessing or robust models can lead to more stable boundaries. Feature scaling ensures that all features contribute equally to the decision boundary. Without scaling, features with larger ranges can dominate, skewing the boundary. Techniques like normalization or standardization are commonly used. Noise in the data, such as measurement errors or random fluctuations, can make decision boundaries less reliable. Smoothing techniques or robust algorithms help reduce the impact of noise, resulting in cleaner boundaries. The amount of training data influences the quality of the decision boundary. With more data, the model can learn more accurate boundaries. Small datasets may lead to unstable or misleading boundaries, so collecting enough data is important. Evaluating your model's performance helps you assess the quality of its decision boundaries. Metrics like accuracy, precision, and recall show how well the boundary separates classes. Visual inspection can also reveal strengths and weaknesses. Cross-validation is a technique for testing how well your decision boundary generalizes to new data. By splitting your data into training and validation sets, you can check if the boundary holds up across different samples. Choosing the right model is essential for finding the best decision boundary. Different algorithms create different boundaries, so it's important to experiment and compare results. The best model balances accuracy and simplicity. Some models, like decision trees, create boundaries that are easy to interpret. Others, like deep neural networks, produce complex boundaries that are harder to understand. Interpretability is important in fields where decisions need to be explained. Decision boundaries are used in many real-world applications, from medical diagnosis to spam detection. Understanding how boundaries work helps you build better models and make more reliable predictions in practical scenarios. To wrap up, decision boundaries are a fundamental concept in machine learning. They define how models separate different classes and make predictions. By understanding and visualizing these boundaries, you can improve your models, avoid common pitfalls, and apply machine learning more effectively. Thanks for joining this journey into the world of decision boundaries.